Okay, so this is the last testing procedures presented in Chapter 7, and it deals with t-distribution, and the difference between the t-distribution and the z-distribution is, well, there's a couple of things. If we don't know the population standard deviation, and that's this symbol, then we usually have to use the t-distribution. I'm only going to ask you t-distribution sample mean questions. I'm not going to make you decide whether you use a z or a t. Because usually we never know the population standard deviation. You can watch a link to a video about William Gossett, who used to work for Guinness Brewery, and he's the one that developed all this. And the other thing you'll see, if you Google this, you'll find the student's t-test. An interesting thing about the name, when I first learned about this, is I saw students. Oh, because I'm a student, that's why I'm using it. It's because Guinness wanted to hold on to his work and not share the results. And it's an interesting story if you want to go read some more about that. So let's get on with this. Do you remember with proportions how we had to do that n times p thing, and it had to be bigger than 10, and n times 1 minus p, and how that had to be bigger than or equal to 10, and then we had to have a sample, a random sample. So that's how that would let you know that you could use the central limit theorem and apply these ideas to this. Well, with sample distributions or with means, it's the same kind of idea. You got to check for a simple random sample or some kind of random sample. And if you have at least 30 pieces of data, the difference between a t-distribution and z-distribution is you can't tell the difference. So if you have at least 30 pieces in of data in your sample, you're good to go. If you don't, then you got to check to see if your parent population is normally distributed. Sometimes you can infer that. For the textbook problems, they'll tell you this. Or we can use that normal probability plot, the thing we did in Chapter 6.4 last week. Okay, so here's a problem I found. Let's see, a certain vehicle emission inspection station advertises the wait time for customers is less than 8 minutes. So that's their claim, right? And the resident skeptical goes out and gets 49 wait times, and he finds the sample mean in the sample standard deviation. So just to bring back, some of you expressed a concern about symbols. So the sample mean, X bar, is 7.34 minutes, and the sample standard deviation, or if you're on a graphing calculator, they call it SX, is 3.2 minutes. Okay, and of course we know n equals 49, so just some preliminary stuff. So can we use these techniques? Well, let's see. I need to have at least 39 pieces of data, and I've got 49 pieces of data, and I've got a random sample, so I'm good to go. I can use these techniques with this. So here's the claim, and I kind of already said that with the last slide. It said the company's claim is that, hey, our customers don't have to wait any longer than 8 minutes. So that's that. So our hypotheses are, oops, let me get a pen going. HO, the sample mean, or the population mean in wait times, is equal to 8 minutes. Remember, HO is almost always a statement of equality, of equals. And then HA, we want to show that it's less than 8 minutes. So this would be the company's claim. That's the claim we're going to try to disprove, right? That's what the skeptic wants to disprove, that claim. So the skeptic is going to want to show that HO is correct, or is careful that he can't reject HO. So I went out to that applet, that same applet, and I made sure I selected mean, and I typed in my sample size and my sample mean and my sample standard deviation. And then I selected test of significance. I said the average was equal to 8, and then my HA was less than 8. And then I calculated it. And oh, you can't see the results, can you? So I still have the page up. It tells me my t-score is negative 1.44, and my p-value is 0.0777. So notice that it does give us a t-score, not a z-score. That's a good sign. And there's the p-value. Just I wanted to show you this because this happens to people. Suppose you went with the wrong HHA. Suppose you said, okay, well, HO is the claim that the company's making that their wait time is 8 minutes or less, and you want to show that it's greater than that. If you were to set up this test in this applet, you get the same t-score because that's not changing, right? Those numbers don't change, but we're looking at the wrong area, and my p-value would be more than half. So a p-value will almost never be more than half. Certain situations with two-tailed tests, but don't worry about that. So if this happens, know that you went the wrong way with your HA, and go ahead and fix that. Okay. We're always looking for a tail area, so it'll either be down in the bottom tail, the upper tail, or both tails. So for my test, I had a p-value of 0.077. Now they don't tell us, I don't think they told us a level of significance with this problem. Oh, tested the 0.01 level of significance. Well, this is much larger than 0.01, so we can't reject HO. HO was the claim that the wait times were not less than 8 minutes. So since the original claim that the company was making did not contain inequality, did we reject HO? No. We say there's not sufficient sample evidence to support the claim that the mean wait time is 8 minutes or less. So that's when they give you all the information. What happens if they just give you the data? So here's a problem about, let's see, mean wait time in a restaurant drive-thru is 84.3. The manager devises a new system that he believes will decrease the wait time. So he initiates this new system and measures the wait time for 10 randomly selected orders. The wait time to provide it. And of course this problem is kind of talking you through it a little bit. We only have sample, remember the conditions were SRS. So we're assuming randomly selected orders, so that's good. And n has to be bigger than 30. Well, it's not. The other condition was, well, if n's not bigger than 30 or bigger than or equal to 30, then do you have a normal distribution, a normal parent distribution? Well, we don't know anything about that, and that's why it kind of says in this problem, you've got to verify that it's normally distributed. So what we did last week is we actually did this normal probability plot, and this textbook that I took this from actually gave us one. And I'm not seeing, it's not like it's following some weird pattern, right? It's bouncing around the line, and we're not seeing any outliers in the box plot. Remember, the box plot outliers look like that. And we could look at a histogram too and see what that looks like. So I think this is close enough to a normal distribution that we could probably use this test. There's some issues with it. I mean, there's an awful small sample, and we don't know factually that the parent population is normal, so we might get an erroneous result, but for this situation it certainly works. So let's assume we've met all these conditions. We'll run the test. So the claim that the manager is making is that this new system will decrease the average wait time. What are our hypotheses? Well, HO is that the average wait time hasn't decreased, and it's still 84.3. And then we're going to assume, I'm going to go with a claim here, and again, I might get the wrong direction on my p-value, and that's something I'll have to check and see. So I think we'll go with HA as being the claim, the manager's claim that it's actually decreased the average wait time. And this is the claim. So with this one, because they didn't tell me the mean and the standard deviation, I selected one mean, I typed in my data. You can copy and paste it into it. It's got to be in a column for this to understand it. Use data. It calculated the sample mean for me, the standard deviation. And I set up my hypotheses. Remember, check tested significance. Wrote in my 2 hypotheses. Remember, you're clicking on that to change it to less than. Calculate it, and again, it chopped the p-value and t-score off. So looking back at the slide, it told me my t-score was negative 1.31. The p-value is 0.1113. So I'm reporting those out. So with that p-value of 0.1113 and I don't remember what level of significance they told us. They didn't tell us. Oh, yes, they did, 0.1. So the level of significance is 0.1. Well, this is close to 0.1, but it's bigger than that. So we can't reject HO, and to put it, the sample data does not support the claim. The new drive-through system will decrease the average wait time. So I hope this helps you do these problems. We'll get some practice. Do those odd-numbered exercises out of the textbook. We'll do some practice in the forums too.